Take a look at this terminal input. If you negate an empty array and compare it to another empty array using the loose equality operator, JavaScript evaluates the expression as true. Or consider the null value. If you ask the engine to inspect its type, it will report that null is an object. And if you compare not a number to itself using strict equality, the engine returns false. When developers encounter these outcomes, the common reaction is to assume the language is built on a series of illogical compromises. These results are the inevitable output of a rigid, deterministic logic. To understand how JavaScript actually evaluates data, we have to map out three core systems: how it allocates memory, the exact steps of the ECMA 262 coercion algorithm, and the physical mechanisms behind type inspection. Mapping these systems allows you to move past observation and begin predicting behavior in any production environment. We start with the execution context. This visual represents JavaScript's memory architecture, divided into two distinct environments to handle different types of data. On the left is the call stack. This diagram shows it as a strict, ordered ledger, tracking the program's execution frame by frame. This is where primitive types, numbers, strings, booleans, null, and undefined, live. Primitives are immutable. Because their size is fixed and known, the engine stores them directly by their literal value, right inside the stack. Reference types like objects and arrays are dynamic. Because they grow and change, they require the flexible memory heap. The call stack doesn't hold the object itself, but a pointer referencing its physical location. Watch what happens during a live variable assignment. If we declare let A and assign it an object containing x equals 1, and then declare let B and assign it an identical-looking object with x equals 1, the engine allocates a completely new, distinct memory address in the heap for that second object. This diagram shows exactly why checking if A is strictly equal to B evaluates to false. The strict equality operator isn't looking at the properties inside the objects. It is comparing the literal pointer 0x001 against 0x002. The rules of comparison are dictated by memory allocation. Primitives are compared by their literal value, while objects are compared by their physical reference. When a developer deliberately converts a value from one type to another, like wrapping a string in the number function, that is explicit coercion. Implicit coercion happens behind the scenes, when the JavaScript engine automatically converts types on the fly to resolve a mismatched operation. The rulebook for this process is the ECMA 262 Abstract Equality Comparison Algorithm. As we can see in this flowchart, it operates like an industrial sorting machine with specific conversion filters. The loose equality operator, the double equals, pushes data through this exact sequence of filters until the types match. Let's trace the empty array paradox. Brackets equals false. The right side processes first. False drops through the toNumber filter, becoming 0. On the left, the empty array enters the toPrimitive filter. It invokes toString, outputting an empty string. The types still mismatch, a string versus a number. The empty string is sent through toNumber, converting it to a 0. Finally, the types match. The engine's strict equality comparator tests 0 against 0, returning true. The perceived inconsistency of the language is actually the rigid, step-by-step execution of the specification's conversion rules. Because JavaScript is dynamically typed, the engine has the architectural challenge of identifying incoming data types on the fly at runtime. The Typeof operator serves as a basic scanner. It reads the primary tag of a value, making it effective for identifying primitive types. But this scanner is also responsible for the historical artifact where Typeof null evaluates to object. To understand why, we have to look back at the original design of the language in the mid-1990s. In early 32-bit architecture, values used a type tag in the lowest bits. 000 was the tag for objects. The null pointer was a literal 0. Its all-zero binary sequence inadvertently included the exact 000 signature of the object tag. Because Typeof fails on null and arrays, developers must use Instanceof to identify complex objects. This diagram shows Instanceof operating not by checking static tags, but by climbing the prototype chain. Creating a date object and checking its type makes Instanceof traverse the lineage upwards. Finding date.prototype validates the check. Identifying data safely requires using the right tool. Typeof for primitives, Instanceof for object lineages. and specialized methods like array.isArray to bridge the gaps. These three systems operate together. Coercion algorithms dictate behavior, but they are driven by the physical memory dualism of primitives on the stack and reference types in the heap. Understanding this architecture leads to a clear professional standard. Always default to strict equality. By using the triple equals, you physically bypass the ECMA coercion algorithms. The engine checks the type first, preventing unexpected evaluations. When you need to change a type, use explicit conversions. Wrapping a value in the number or string constructor keeps data readable and entirely predictable. The specification leaves only one acceptable use case for loose equality, writing x equals null. This acts as a deliberate idiom that efficiently catches both null and undefined in a single check. For extreme edge cases dictated by the IEEE 754 math standard, like distinguishing -0 from +0, or proving that nan is actually nan, the precision tool is object.is. Relying on trial and error to force the syntax to behave will always create inherently fragile, unpredictable code. True mastery of JavaScript comes from aligning your code with the physical and algorithmic truths beneath the syntax.